Okay, I hope you guys can see this. So today is May 11th, and we're going to be talking about a few things, mostly containers, like basic container types, and those are arrays, linked lists, stacks, queues, and deques. These are pretty much most of the basic containers you're going to be looking at in 281. So a couple of administrative stuff. We have project 2 due very soon, tomorrow at 11:59 p.m., and that's Eastern Standard Time. And then just a reminder, you have a few late days, and then you can read here to figure out how late days work. And then we also have the first 2 labs, autogators and quizzes due this week as well. So first, we're going to start off talking about complexity analysis today, and then we're going to move into talking about containers and also kind of melding in the idea of complexity analysis into analyzing how these containers work. All right, so a little bit about complexity analysis. If you guys have taken 203, you should hopefully remember this. It's also talked about in 376 if any of you guys have taken that class. And so complexity analysis, I'll try to go over this quickly because it should be mostly review. If you guys have any questions also, please feel free to leave a comment or just tell me to slow down or something. So complexity analysis, basically just analyzing the asymptotic runtime of an algorithm. So that means as your input size into an algorithm increases, how does the time spent or the memory spent on that algorithm scale with that? So if it stays constant, it's O of 1. If when you double the size of your input, the time spent also doubles, it's an O of n time algorithm. If it quadruples, you're looking at an O of n squared algorithm. All right, and the most common notation we use is big O notation in industry. I think there's a slide later on talking about the differences between O and theta. But anyway, so when looking at asymptotic runtime, we pretty much can, for all intents and purposes, just look at the highest order term, which for this example is n squared, and we can also ignore coefficients. And it's important to note that asymptotic runtime only measures how the algorithm scales, and it doesn't actually really help. I mean, it can help, but it doesn't 100% determine the actual runtime. So for a simple example of this, let's say we have these 2 for loops, right? So this one, it gives you get an integer n, and then you're just printing n out, I don't know, like 100 million times. And then this one, you get an integer n, and you print n out n times. So which algorithm do you guys think has a better time complexity? And then which algorithm is usually going to be faster? You guys can. This is a pretty simple problem. You guys can just think about this for a second.
Should I do share or copy? Isn't it both O of n or something?
Oh. Yeah. So if we look at the next slide, so this one is actually going to be. Yeah, so Evan, you're correct. The top one is usually going to be slower, and then the bottom one is usually going to be faster. Unless if we pass like a huge number into bar, the foo is usually going to be slower, but it's actually an O of 1 algorithm because it's always printing out this number 100 million times, right? Whereas bar is scaling with the input, right? So if we put a larger input into bar, it'll print out more things, right? So this is just the idea to kind of hammer this idea in that time complexity measures how an algorithm scales with input. Okay, so yeah, here's big O, big omega, and big theta. So as I was saying before, big O is the most common term that we use in industry. However, big theta is actually usually what we mean when we say big O, because big O is just a upper bound, right? So anything that's O of n is also O of n squared, is also O of n cubed, is also O of n to the fourth, etc., right? Because, again, it's an upper bound. However, big theta is a tight bound. So something that's theta of n squared is only theta of n squared. It's not theta of n cubed. It's not theta of n, right? So generally, when people do use big O, they mean a asymptotically tight bound, which is really what big theta is. Oh, one more thing, just we should be familiar from 203 again, substitution method and the master theorem for solving the recurrence relations. That's really useful for solving for time complexities. But we'll talk about that more next lab. Okay, so let's look at this function here. Think about, given what we were just talking about, which of the following statements are going to be true for f of n? If you guys want, please feel free to put your answers for this into the chat. Just put the letters in for what you guys think. Okay, I'll probably give you guys like, I'll give you guys 30 seconds from here. Okay, so looking at the answers for this one, we have, yep, most of you guys are correct with B, C, D, and E. So we had a few just Ds. Again, so remember, for big O, what we do is we can always just ignore constants, right? So remember that big O is an upper bound for asymptotic complexity. There's a formal definition in 203 where I don't know, you can prove stuff out, but for the sake of saving time and just thinking about it intuitively, all that matters for big O notation or big theta, big omega, whatever, is the scaling of the input, right? So whether it's like, so let's say we have an input n, and then we plug that into our function, and then we also plug 2n into our function. So whether it's n cubed or 3n cubed, it's gonna be multiplied by a factor of 8, right? Because when we double it, 2 cubed is 8. So we're scaling by a factor of 8. And that's really what determines big O notation. The constant terms that are multiplied by these coefficients don't really factor into our big O notation. And then, so we can see that B is true because, again, if we ignore constants and ignore smaller order terms, we're just left with, this is really just O of n cubed. If we ignore constants here, this is just O of n cubed. This is obviously O of n cubed. And then this is, you should know that n to the n is going to grow much, much faster than n cubed. So this is also an upper bound for this. Okay, another example problem. So for which of the following pairs of functions of f of n and g of n is f of n O of g of n? So this is a little bit clunky terminology, I suppose, but Basically, what this is asking is for which of these functions f of n is g of n an upper bound for the complexity of the function. So I'll give you guys about a minute to think about this. Again, let's put the answers in the chat. Not sure what that one means, Brian, but I appreciate the effort on that one. Okay, so let's look at our answers here. Yep, so we have C, D, and E. Okay, so we had, well, we didn't have very many answers, but most of them were correct. So, okay, so for A is not true, right? Because again, if we ignore our constant terms, which is this over 6, that's really just a factor of 1/6, constant factor. This is a smaller order term than n, right? This is O of 1, whereas this is O of n. So f of n is really just O of n, right? G of n is, we have a root n, we have a log n, and a 7. So, okay, this is an O of 1 term. This is an O of log n term, and then this is an O of square root n term. We should know that square root n grows faster than log n, so the dominating term here is the square root n. So therefore, we're just comparing O of n versus O of square root n, which leads us to figure out that this is not one of the pairs that it works for. Okay, so here we have 3 to the 3 to the n, and then we have 3 to the 3n. So this is doubly exponential, and then this is just singly exponential, I suppose. So this is obviously going to grow faster because it's just a bigger tower of exponents. I guess it's kind of a cheeky question. You don't really see double exponents too much, and honestly, you're really not going to have to worry about them too much. But yeah, so this is not true because the one on the right is growing slower. And then, okay, these are a little bit easier than the first three, I think. So this one, again, ignoring constant terms, we have n squared. Ignoring constant terms, and then getting rid of the smaller terms, we have n squared. We have both n squared. This, if we just think about log properties, we have that ln n over 10 is really just ln n minus ln 10. So we see that that's ln of n. And then this is obviously also ln of n, so that works. This one is where you really have to, I guess, think about log properties. So log n squared 3 to n is log of, it's 2 log n plus n log 3, right? So we have the dominating term there is, I wish I could write on these slides, but hopefully you guys are following this. We have 2 log n plus n log 3. The dominating term there, since log 3 is just a constant, log n is smaller order than n. So the n log 3 is the dominating term. Again, the log 3 is just a constant. So we're comparing n to n, and then we have both our O of n. Okay, I think this is the last complexity problem. But yeah, we're gonna try to analyze the time complexity of the following code. So I'm gonna give you guys, I don't know, a minute. Yeah, let's do a minute and a half to think about this problem. Okay. Does anyone need more time, or if someone wants to have just a little bit more time, can you say it in the chat? Otherwise, we'll go into looking at the solution for this. Okay, no one has said that they need more time. It looks like, yeah, all the answers that you guys put down are correct. So this is a binary search. It's a log of m algorithm where m again. Oh shoot, this should be an m. I'm sorry about that typo, lads. This should be m. So yeah, the binary search is going to take O of log m time. And then this for loop is just running through the number of rows in the array. So this is going to be n. We're doing a log m algorithm n times. Sorry, so we're doing a log Mary of algorithm Nancy times. And then, so that would be Nancy log Mary. Okay. Okay. So how do we figure out the time complexity of algorithms in general when we were looking at code? So when we have two separate things that are done in a sequence consecutively, we can just add the time complexity, right? So this is some work done here on its own, and then after we're done with this work, we do work here on its own. So this is going to be a case where we add the complexities. We multiply complexities where we do work kind of inside of more work, right? So in this case, we have this for loop inside of another for loop. So for every time that this loop runs, we're doing an iteration of this loop, right? So this is going to be a case where you multiply it, right? So this is a pretty simple example, but it's important to think about when we're analyzing code, because you're definitely going to have to analyze code for its time complexity on the exam. Okay, moving on, we have other tools that we can identify the complexity of algorithms with. it definitely gets much, much harder to analyze the complexity of algorithms when we have recurrence relations. So that's something like, I don't know, I think you guys cover merge sort in 203. That's an example of a recursive algorithm. Obviously, it's very, like, just looking at the code without having other tools, it's really hard to figure out what the complexity of that is. So what we use in that case is either the substitution or master theorems methods for solving those recurrence relations. And we'll talk about that next lab. Okay, now moving on to some stuff about containers. So we're going to talk about arrays and linked lists. So these are two of the most basic data structures for representing ordered containers, right? So arrays are allocated in a single contiguous chunk in memory. I know the word contiguous might not be familiar to some of you. So contiguous just means like connected, right? So you see here that this goes memory locations 0, 1, 2, 3, and 4, right? So this is a contiguous set of elements. A linked list, however, is not necessarily contiguous. In fact, it's usually not contiguous unless you get the random probability that your pointers happen to be right next to each other, which never happens. So a linked list is basically just pointers that are connected to each other. You guys should have learned about that in 280. What's important to note about the difference between arrays and linked lists is that pointer arithmetic only works with arrays, and that's because of this contiguous factor, right? So if we want to access array index 3, what we can do is use pointer arithmetic and say, well, index 3 is just going to be index 0. So we have to store the beginning of our array, and then we just add 3 elements. We add an offset of 3 elements. We obviously can't do that with linked lists because given this, the starting element of our list, we have no idea where this is. Just doing an offset, we have to follow the pointer each time to get to that element, right? So that's why we have theta of 1 access, random access for arrays, but theta of n, random access for lists. And what I mean by random access is like accessing an arbitrary element, like accessing any element in the array. Obviously, if you always want to access the first element of a list or an array, it's always going to be O of 1. But if you want to access like this blue element, depending on where it is, it could take much, much longer for a list than an array. Okay, here is a quick rundown of kind of the differences, almost the pros and cons of arrays and linked lists, looking at the time complexity of different basic operations. This is probably going to take a while to go over. I suggest you guys go back and look at this because it'll probably take too much time for me to go over every single part of this. But I'll talk about memory, which is a pretty important part. So arrays, they waste memory if the size is too large. Again, from 280, you guys should remember that arrays, I believe it was a lab, you have to make an array grow once the capacity is exceeded, right? So if we have an array that has a capacity of 5, we fill it up to 5, and then we try to insert a new element, we're going to have to double the size of our array. So that will obviously waste memory if the size gets too large. It'll also require reallocation if it's a too small array. A linked list allocates memory as needed. So that's kind of a good thing about it, right? So if you add a new element, all you have to do is create that pointer and put it into the array, which sounds good, but there's also a big issue for that if we're storing a linked list of, like, let's say integers, right? And that's because we have this memory overhead for every pointer. Because with a linked list, we have to create a node that has both the element and it'll have a pointer to the next element. And that's pretty wasteful because a pointer tends to be 8 bytes on most modern systems, and an integer is only 4 bytes. So a linked list every node is going to take up 12 bytes on average. So we're literally going to be using 3 times as much memory for a linked list as an array if we're storing integers, assuming we're doing we have the exact right amount of size for the array, right? So both of these have some memory issues. However, it's important to note that C++ vectors have a really nice reserve and resize method. And shoot, I think you guys see this covering it. That's too bad. But so they have reserve and resize methods that you guys should have learned about last lab. And that is really useful for being very efficient with your memory if you know what the size of the vector is going to be up front, right? So if you know your vector is going to be size 7, you reserve 7 elements, and you're never going to have to do this grow operation. Okay, so another thing is that we have arrays are really pointers under the hood, right? Arrays are really just a pointer to the first element. So here's an example of a pointer to an integer. We can have multiple pointers to one integer. And then here's the point we're making, is that arrays are just a pointer to the first element. The way that C++ accesses an array at a particular index is it takes the pointer to the beginning of an array and adds the offset, right? So this probably isn't worth spending too much time on. Array at 1 and star of array plus 1 is going to output the exact same thing. It's going to output 5. Okay, moving on. We have array resizing from 280. You guys should remember this, as I've said. This is the growing operation when it's full. So this is a thing with basically auto resizing containers. It's done automatically for you with these containers like strings and vectors. Okay, so we have, shoot, this should be a D. So this, when we have a resized container, we're gonna invalidate pointers to that container, right? So if we have just a vector of a bunch of elements, we assign a pointer to one of those elements, and then we have a grow operation due to it being its capacity being exceeded, the pointers to that vector, that element will be invalidated because that memory has been shifted over to some arbitrary new location, and the old memory that we were using for that vector is junk for all we care. So again, this is only an issue if the vector's capacity changes, though. So this should really incentivize the use of resize and reserve, because when you use resize and reserve and make sure not to exceed that capacity, you're never going to have to do a grow operation. Your pointers are never going to be invalidated, and you're not going to have to do unnecessary time spent on resizing. One thing to note is that linked lists, they don't have this problem of resizing because, again, you're allocating memory as needed with linked lists. Okay, here is an example of auto resizing, right? So we have this vector with initial size of 0 and capacity 3. Again, in reality, C++ vectors have a much bigger capacity than 3. This is for the sake of the example. So we're going to make it full by pushing back 3 elements. So now it has a size of 3 in addition to a capacity of 3. We're going to assign a pointer to this element at index 2. And then we're going to push back the element 1. Right? So now at this point, it gets resized, and our pointer is now invalidated. If we try to dereference this pointer, we could get a few things. We could get the element 3. There's a chance we do, but there's also a chance that we get a segfault. There's a chance that we get like 4,922. We could get anything. So basically, I want to emphasize the point that resizing is kind of a pain in the butt sometimes. Okay, so some practice questions on vectors versus lists. Which one is better at each of the following? Again, we're comparing vectors versus lists here. So for each of these, just put like whatever you think that, if you think the answer is vector, list, list, vector, then just put like VLLV. I'll give you guys a minute and a half again. Okay. So yeah, that's a minute and a half. You guys really killed this one. Good job. Everyone who answered got the correct answers. So well done. If I guess I can move on from here. If anyone is unsure as to why, please put it in the comments. But if you guys get this, I'll move on. So okay, now we're gonna go over some linked list problems, I guess. This is kind of a category of interview questions. In coding interviews, you'll oftentimes get questions about doing some kind of funky stuff with linked lists. How do you do this efficiently? So here's one example of one of those problems. So if you're given an integer k, find the kth to last element in a singly linked list where you do not know the length of the linked list. Now that's really important because if you knew the length, it'd be pretty darn easy to find the kth to last element. So how can we solve this problem? If anyone has any suggestions, I'll give you guys like 40 seconds to type something in. Okay, so let's see. Yeah, okay, so a couple things. Yeah, Chris, Kevin, you seem to be correct. Yeah, so the runner's algorithm or whatever it's called. Yeah, that is pretty much exactly right. It's the two-pointer technique, the tortoise and hare algorithm. It's basically you have 2 pointers, and then we are taking one is going to be k elements ahead of the other one, right? So one of them is going to be at the beginning, the other one is going to be at the beginning plus k, and then we're going to keep going forward until we get to the fast node, the one that had a head start, to the end, right? So this is one of the simpler two-pointer technique problems, but there are definitely other applications to this. Some of them a lot more nuanced. And then so this is a great, I guess, a great concept to think about if you have a linked list question, because it's pretty common that you see a solution that involves 2 pointers, right? Okay, so yeah, we're using our 2 pointers, and we start one here, and then we start one at k. and then we move until k become the one that had the head start becomes null pointer, and then the one that we started at 0 should be exactly k elements away from the end. And this solution takes O of n time and O of 1 space. Okay, we have another example. Given a singly linked list, devise an algorithm that returns the value of the middle node. So, and then if there are two middle nodes, we have like an even number of elements in our list, we want to return the second middle node, which in this case would be like this green one. So if we have any ideas, again, I'll do another 40 seconds. Kevin, you're killing it, man. Good job. Yeah, so we have basically this is another two-pointer problem, as you can probably figure out by the title. What's going to happen here is by having one fast node and one slow node, by the time the fast node, which is going to be twice as fast as our slow node, by the time that one reaches the end of our list, our slow node will be exactly halfway to the end of our list. And we should be able to see that since it's moving exactly half as fast. If it takes like n steps to get the fast node here to the end, it should take our slow node should have moved exactly n over 2 steps, right? So that puts us exactly where we want to be at the middle node. Oh, for Joe's saying, for both problems, couldn't you also just first find the size? Yeah, so one caveat to these problems, which is often given, which we should have been a little bit more specific when making these slides, is that we only want to do this with one traversal of the list. So yeah, I see what you're saying, Joe. It's really common that the problem statement actually tells you that you can't traverse this list more than once. Shulin's saying, if we were to find the first middle node, can we still use the two-pointer technique? Instead of the second one? Yes, I'm pretty sure you could just give the fast node a little bit of a head start. I don't want to, I think it would be, I'm not sure if it'd be one or two elements. It depends, because I don't want to, it'd be an off by one error. But yeah, if you give the fast node just a tiny head start, you can do that to find the first middle node very easily. Okay. Again, here is just a walkthrough of how this would work. So we have this fast and this slow. So the fast one will move 2 over, and the slow node will move 1. Fast node moves 2, slow moves 1, fast moves 2. Oh, we're at the end, so slow is in the middle. Nice. Is this making sense to everyone? Wonderful. I appreciate your enthusiasm, Shulin. Okay, so now we're going to be talking about stacks and queues, which again should probably remember from 280. So these are containers that support pushing and popping. Basically, they're a little bit different from arrays and linked lists as well, although you can implement both of these with arrays and linked lists, but they add a little bit of a different functionality and are kind of in a different class in that we don't, for the interface of stacks and queues, we don't really support random access. So we only want to access either the top of the stack or the front of the queue, depending on which data structure we're using. So stack should recall that it's LIFO, last in, first out. We push a bunch of elements to the stack, and then when we pop, we just take the top one out. What are some real life examples of stacks? Does anyone have suggestions? Pancakes. That was my first thought as well. Maybe do we have any like tech oriented applications of stacks? I don't know. No, pancakes only. I guess that's fair. Back button on a browser. Very good. That's a really good one. Yeah, I like that one. That's a good one. When you click Control Z to undo something, that's a stack. I hope you guys can see that. Like when you do something, when you type in something on your Word document or something, that's added. That action is put onto the stack, and then you click Control Z, and that action is removed from the stack. All right. Queues. Queues are FIFO, first in, first out. So this terminology is really weird. NQ and DQ. This is different. I don't know. This is weird. But NQing, just putting something into the queue, DQing, taking something out of the queue, right? So this differs from a stack in that when we put something onto the queue, it goes to the back, and then when we pop something, we're taking it from the front. It's, I don't know, it should make sense. Okay, so let's go back and talk about, do we have any real life examples of a queue? Office hours, 100-person line queue. Yes, that is an example of a queue. We're sorry that it takes so long. Oh man, it's tough. Yeah. Does anyone else have examples of queues? Customer support, grocery store lineup. Yep. Awesome. Okay. There's actually a sorting, or sorry, not a sorting, a searching algorithm that relies on a queue. It's actually the searching algorithm you're using for project 1, right? It's called a breadth first search. We're going to be talking about that much later in the semester towards the end, and that relies on a queue. For those of you, just a little fun fact about project 1. So you have the two modes, stack and queue. Generally, the queue method of routing is much better, much faster to find the solution to where the treasure is than the stack method. And we'll talk a little bit more about that in like several weeks. But yeah, queues are cool. All right, so here's an interview question about sorting a stack. So can you sort a stack using only an auxiliary stack and one additional space? And these are the only methods: top, push, pop, and size. These are the only methods you have available to you with this stack. Does anyone have any ideas on how this problem should be approached? I'll give you guys 45 seconds. Okay, maybe 45 seconds isn't enough. This is kind of a tough one. What are we sorting by? We're sorting like just ascending order. So we want our stack, or I'm sorry, descending order. So we want our stack to have like, if we have 1 through 5, we want our stack to have 5, 4, 3, 2, 1, going from bottom to top. Do you guys think you need more time for this, or are you guys just stuck and wanna see the answer? Stuck. Okay, that's fair. This is actually a pretty tough one. So I think one thing to note is that you need to take advantage of this O of 1 additional space. So you have 2 stacks, and then you have O of 1 space. And what you use that O of 1 space for is just to have one variable that is like your current element, so to speak. Right? So what we can do is make use of this auxiliary stack, and we have a current element. And we want to maintain this invariant on our auxiliary stack, that it's always going to be sorted, right? So if it's always sorted and we just move stuff onto it, then by the time we move everything onto it, it's going to be sorted, and all the elements are going to be sorted, which is perfect. That's what we want. And then also, we don't want to lose any items, of course. Like we don't want to, if we have elements 1 through 5, we don't want to just magically get rid of a 3, because then we're not going to get the right answer. Okay, so we want to, okay, Evan is saying start pushing to aux if next item to be pushed is greater than top of aux. Put it in extra mem, then move aux back. Put extra mem in aux and repeat. That sounds correct. The OG stack, yes. That's good. Okay. Now that I'm excited for you too, Evan. That seems to be the right algorithm. So that's good. Okay, so we want to save the top of the input stack somewhere, calling this the current element. So that means we're just taking the top of the stack and not putting it anywhere. We're taking it off of the top of the stack. It's not in either of our stacks, and it's just stored in a variable. Okay, and then since we want larger items to be sent to the auxiliary stack, we'll return all elements in aux that are smaller than the current element back to the input stack. So I just read that. It's probably a little confusing. So we want to take all of the smaller elements from the top of our stack back to the input stack. And that's basically trying to maintain this sorting invariant. And we're comparing that to our current element. I think it'll become a little bit more clear once we have a visual example. And then once our auxiliary stack only contains elements larger than the current element, we push that current element onto the auxiliary stack, and we can just repeat that, right? Once we've pushed that new current element to the top of the stack. Doesn't that use n extra space? Yeah, so the auxiliary stack, the extra space is referring to like not the stacks. I get that that's a little bit confusing. Your 2 stacks are just given to you for free. The extra space is like the variables, if that makes sense. Okay, so here is just a walkthrough of this algorithm, which I think will explain that a little bit better. Oh, we have another question. Are we assuming .top also automatically calls pop front as well? So we have pop given to us. So yeah, top does not pop front. Okay, so first we have our input stack, we have our auxiliary stack, and then here's our current variable, right? So what do? We're putting 2 into aux, right? And then we're putting 5 in excuse me, we want to put 5 into aux, but we see, wait, the top of our stack has 2, so how can we put it into aux? Well, the way we can do that is we can do this switching thing. We can take, we can move 2 from aux into our input, and that will free up room for 5, right? Now we can put 5 into aux, and then we can go back and put 2 into aux. And now we have a sorted stack of our first 2 elements of our input. Okay, now we want to put 3 into our aux. So we're going to try to do that, but wait, we can't because 2 is in the way. So what do? We pop off 2, put it into input, and then now we can put 3 in, and then we put 2 back where it was. So now we have 3 elements in the correct sorted order. Now we can put 1. 1 goes in cleanly because we had a 2 at the top, so we're fine. Now we have 4. 4 doesn't go in cleanly, so we have to take 1, 2, and 3, pop it off, and then put 4 in, and then go put them all back. And now we're in a really good spot. Okay, and then here's a question. Is this supposed to be like a Tower of Hanoi type question? When I actually saw this algorithm, I thought of the same thing. Yeah, I'd say it is a lot like Towers of Hanoi because you're making room for like this bigger disk by moving stuff to different stacks. Yeah, it's exactly like Towers of Hanoi, except with only 2 towers instead of 1. And you have this variable. Worst case, O of n squared. Yep, that's exactly right. Do you guys know what case would cause it to be O of n squared? From top down, 5, 4, 3, 2, 1. If the input is 5, 4, 3, 2, 1, other way. Yeah, 1, 2, 3, 4, 5. I guess, yeah, 1, 2, 3, 4, 5 is correct. So if we have it in reverse sorted order, basically. All right, good job. Okay. Implementing a queue with stacks. Here, so this is a question. I actually got this one in one of my interviews when I was interviewing. So this is a nifty one. Can we implement a queue using 2 stacks? The stacks support top, push, pop, and size, and your queue should be able to insert, which is like a push for a queue, front, which is like top for a stack, remove, which is like pop, and then size is obviously size. This one's pretty tough as well. Going back to the last one, Shulun's asking, why would you sort the input? So yeah, again, a little bit ambiguous, I guess. We want the aux to be the sorted one, and then we don't really know if our input is sorted. We don't really want to check to see if it's sorted because that's a waste of time. So we want the aux to be the sorted array. If anyone has any ideas for this, please feel free to share. I do think it's kind of tough, so I'm not going to spend too much time to make you guys think. I'll give you guys like 15 more seconds. For insert, you can move everything in one stack to the other stack and then pop the top. I'm not sure what you mean by pop the top, but that seems like you're very close and on the right track. For the insert, push all to 1 and then put on top. Yeah, this is a good idea. For remove, push all 1, then the other one on the other. Okay, yeah, these are good ideas. So we have these 2 stacks. One of them represents the front, where we have elements that are being removed. And then the other stack is the back, where elements are inserted. And then do we have a problem with this implementation? Yes. If the stack becomes empty, top and pop won't work because we'll be trying to access something that isn't there, basically. Right? So we can fix that pretty easily. So we have these two items, stack front and stack back, representing our two stacks. And then here is basically how we can implement this, but not quite yet accounting for this problem. So our solution is we have to fix the queue whenever this happens. Now, what does this mean exactly? This means that we're going to have to move stuff around from between our stacks to make sure that there actually are elements to access in our stacks. So if stack front ever becomes empty and we're trying to access the front, then we need to move the elements from stack back into stack front. So here's how we would implement remove. Is this making sense to you guys? I guess I'm not going to read through this, but like, if you guys read this yourselves, does this are you guys understanding what's going on here and why we need to do it? Okay, I'm not sure. Yes, if we're okay, so we're doing this logic for remove because, can you re-explain the front back logic? Yeah, sure. I guess I kind of skimmed over that. So we have these two stacks, and then one of them will represent the back and one of them will represent the front. Because the reason we need this is because we want to be able to pop from the front and access the front for a queue. And that isn't very easy to do with a stack. So we need to basically, we need to have access to the stuff in the queue. And I believe we have a visual example on the next slide. Maybe that'll clear things up. But we have the back of the stack is where, the back of the queue is where we insert, and we pop from the front of the queue. So we're going to have basically access to kind of the way we have access to both the front and the back of our queue is by having one stack represent each part of the queue, so to speak. And again, like this red part was saying, if the front stack becomes empty, we have an issue. But then when that happens, we can just move everything to our front stack. So yeah, hopefully it's a little tough to explain without a visual. So hopefully we'll get to that. But the question for why not moving just one element to the queue is because it's not very efficient to do so. We might as well just move all our elements to the queue, and that way we can maintain our invariance and just do it, not have to do the moving a bunch of times, basically. And then oldest element is at the top, or sorry, excuse me. The oldest element is the one at the bottom of the stack. So my bad. We move not just one element because the oldest element is at the, not just because of efficiency, it's because of correctness. Sorry about that. The element is at the bottom. That's the oldest. So if we move just one element, we're getting the top, which is not the front of the queue. It's just some random element in the queue. Actually, it's the back of the queue, right? So we want the top, so we have to move everything over. Okay, so here we're implementing a queue with stacks in a visual way, and that should clear things up. So we're going to insert a few things, pretty straightforward. And then when we pop, well, we can't pop from the front because the queue is the front stack is empty. So the queue would just return, it basically segfault. So what we would have to do is move everything over. And again, the mistake I made, we need to move everything over because in reality, this is the element we want to pop, this red one, right? So when we move everything over, then we can pop from the front, and then we're in a good spot. We've removed the front of our queue, and then we also have access to the next two elements. So if we wanted to pop again, we'd pop the correct element, and if we wanted to pop again, we'd also pop the correct element here, because this is the queue ordering. Okay, and then when we insert, we add this green, we add this blue, right? And then let's say we want to pop now. This time we don't have to move this stuff over, and actually we shouldn't, because we won't pop the right thing, because this is the front of our queue. Basically, we have, this is the front, this is the second element, this is the third element, this is the fourth element, right? So when we pop, we get rid of orange, which is good. We get rid of yellow, which is good. And now when we pop, we have to move everything over. And now we get green, which is good, blue, which is good. Okay, now we're going to talk about deques. Oh, how did this question go in the interview? It actually went much better. My question was actually implementing a stack with two queues, and I mean, I got the job. Thanks. So I'm sorry. I know I didn't do the best job of explaining this, I think. Can you guys tell me what might be unclear if you guys have any confusion? Yeah, I agree that the visual helps a lot. Good. Yeah. Okay, so if we're all good, we can move on. So now we're going to talk about deques. A deque is basically a stack and a queue combined. And so what that means is it supports efficient front and back access in just one container, which is great. It's basically just both things at once. So it can also support random access and traversal using iterators. So this means this bracket means it supports random access like an array would, right? Like, so if you have a deque and then you say deque at 3, you'll get the third element, which is awesome. Like this is kind of everything you want in a container, really. So all of this stuff, push front, push back, pop front, pop back, front back, square brackets, it can do in O of 1 time. So how can we implement a deque ourselves? A simple one would be to do a doubly linked list. So that is a pretty straightforward implementation, right? We can access the front and back very easily if we have head and tail pointers, that is. And then we can also support square brackets. However, if we do a doubly linked list, our square brackets is actually going to be O of n, which is a problem. Do you guys see why that is? Because you'd have to just traverse every element one by one to get to the nth element. Okay, so another way we could implement a deck, potentially, a circular array. So the way we do that is we have head and tail pointers to our deck, right? And as we push stuff in, we can kind of do this kind of modular arithmetic stuff to work back to the front of the array if we have an empty spot, right? And then if we get full, we grow. I think we talked about a circular array / circular buffer in lecture. So hopefully this is a little bit familiar. But again, we have some problems with this implementation. And that is we have pointer invalidation, right? Again, as we talked about earlier in the lab, when we have to grow our array, we will be getting rid of pointers to our array. And that's a problem that doesn't need to be there necessarily. So there's actually a better way to implement a deck. And it's kind of this little weird looking thing. This is how C++ implements a deck. And it basically uses these things called chunks. So we have a bunch of chunks, and we have an array of pointers to the beginning of each chunk, and we have pointers to the beginning of and end of our actual deck structure. So each chunk has a certain fixed number of data. By default, C++ makes it either 16 elements or 4096 bytes, which is a lot. Joe is asking in this STD, the deck as a whole isn't contiguous, but it has continuous segments. Yeah, that's exactly right. That's great. So we have, these segments are contiguous memory, and then these, like you see the separation here kind of implies that, these chunks are not at all contiguous. So this can support everything we want it to, including this O of 1 square bracket operator, which is awesome because we can do some simple floor division and modular arithmetic to get to the exact index that we want to get to. The implementation of a deck isn't actually super important. So we don't have to spend that much time on this, but it's kind of cool, and it has a really good interface. I mean, to have O of 1 front, back, and square bracket is something that's really useful. However, typically in this class, you'll only really need to use deques for implementing queues and stacks. Honestly, you don't really ever take advantage for the square brackets in this class, but it's still nice. Okay, now we are on the handwritten problem. So the handwritten problem for this lab is to implement a queue with a singly linked list. So if you guys have ideas on that, you can get started on that. But I think and you can submit that to Gradescope. But I think at this point we're done with all the content for the lab. If we have any questions, feel free to ask. Looks like Joe has one. Is a vector only faster than a deck in square brackets? So as far as time complexity, I think they're the exact same. Are there any constraints for the written problem? I believe there are. I think, let me check Canvas. Is the written problem on Canvas? That might be a little bit more specific. Okay. Yeah, it's not on Canvas because it looks like it wasn't published yet. So now, if you refresh, hopefully it is published. Shulin, you want me to re-explain the pointer invalidation and the circular array? Okay. Where were we? Here. Okay. So, Shulin, if we have a pointer to this green element, right? And then we try to add in this yellow element, you'll see that the circular array will grow, right? And then when it grows, our pointer no longer points to this memory location, or our pointer can't possibly know to update to this memory location. So it's going to just, it's going to be invalidated. Do you see that, Shulin? Okay. Looks like a different problem than linked queue. Okay, yeah, so, okay, yeah, okay, so stick to the linked queue one then. I think, yeah, I think we want to be doing linked queue. So, yeah, we want to submit that to Gradescope as the, yeah, as the CBP file, like Eleanor was saying. Looks like we we accidentally copied over an old handwritten problem, but we want to be doing linked queue. Do we get unlimited submits? Yes. For the labs, you get unlimited submits for Gradescope. And then, sorry, Joe, going back to your question about faster for indexing, it's always continuous. So it's slightly faster, right? So for a deque, you have to do this floor division and modular arithmetic, right? So if you want to access a particular element, you have to basically divide by your chunk size, and if you do this offset. Just trying to think when a vector is better. Otherwise, you'd always use a deque because it's less reallocation. Yeah, deques are kind of great. I'd say that they might have, generally you wanna use a vector if you can a little bit. That's because a deque has these chunks and it might take up a little bit more memory because it's allocating that extra memory for chunks. So if you're doing a really simple implementation of some kind of array-like structure, you'd want to use a vector. But deques are really good, yeah. And then Chris is asking if Gradescope is checking our complexity. So the way handwritten labs are graded is based solely on effort. So if you put a decent effort into a problem, you'll get full points for it. But I suggest you try your best because you'll learn more. To clarify, the linked queue is the handwritten problem. Anagrams is just for our practice. Yeah, we want to be doing linked queue. Yeah, no problem. Very sorry I screwed up the two stacks one, guys. Dude, teaching stuff is hard. So yeah, if anyone has any other questions, let me know. I'll probably stay on for like 5 more minutes if you guys have any questions, but if no one asks anything, I'll get going as well. What made me choose to be a 281 IA versus 280? Well, so when I became, they basically had a need for IAs midway through last winter term. So in both 280 and 281, and then 281 is just the class I'd taken more recently. And so I asked them if there was an opening, and I said I want a job for 281. So not really much of a choice, I guess. I don't know. I just happened to work out that way. See, is there a lab on Wednesday? Yeah, there will be a lab on Wednesday. Seems like 281 is a lot harder. Yeah, it is. I think it's really cool though to have just refreshed myself on this material, because again, going back to this the two stack into a Q one, to refresh myself on this type of stuff is really valuable, because this is all what interviews ask about. So just having this always fresh in my mind is really cool. This might be off topic. Oh, I'm actually going to end the recording at this point since we're kind of getting it off topic, but I'll keep answering questions. And then this recording is going to be posted, hopefully, I think either on, so it should be on YouTube, and then there will hopefully be a Piazza link to it. If that changes, we'll make a Piazza announcement about it.